We're continuing on from the previous video, looking at equilibrium and our second example. So here we've got a ute in neutral cruising down a hill. The hill is 50 meters long and we're asked to find how long it takes to reach the bottom. We're neglecting frictional effects and assuming the ute starts from rest, so initial velocity is equal to 0. So first we need to resolve forces acting on the ute in the x and y directions. So we know our weight acts through the center of gravity, so that's our weight equals mg. Our friction is up, and that's our normal. Of course, friction is 0 in this example. We don't need to consider that. So we've got our weight downwards. We need to resolve the weight force into its components down the slope and perpendicular to the slope. So the weight force is mg. That's the component down the slope, and that's the component perpendicular to the slope. We've got theta here, which we saw was in the example. We're just going to call that the variable theta. It's not defined as a value, so this will be mg sine theta, and this will be mg cos theta. So we've got our weight component down the slope, which is what we need. Weight, I'm going to call that x equals mg sine theta. So that's the force that we need. We're going to be using Newton's second law, which is F equals to ma. So our net force is down the slope with the value of mg sine theta, which is our wx. So mg sine theta equals ma. So our acceleration is g sine theta. Now we need to use another law of motion of Newton's, which I introduced in the previous video as s equals ut plus half at squared. And we use this to find the time that it takes to go from the top to the bottom of the hill. We know s is the length of the hill, u is the initial velocity, t we need to find, and a we just found by breaking up the weight force into its components. So that's the acceleration down the slope. So 50 meters equals 0 plus